All right, let's jump right in. In this explainer, we're unpacking a concept that is, honestly, absolutely staggering. It's based on the groundbreaking insights of theoretical physicist Dr. Michio Kaku. Now, we all know digital computers have changed virtually every aspect of our lives. But what we are looking at today is a shift so profound, it makes the digital revolution look like a minor stepping stone. Compared to what's coming, our current laptops and smartphones are basically glorified abacuses. We're right at the initial stages of a massive historical leap for humanity, the arrival of quantum computers. These are the ultimate machines. They don't compute on plastic and wire, they compute on atoms, the fundamental building blocks of matter itself.
Okay, here's our quick roadmap for today. 1. The evolution of computing. 2. Enter the quantum era. 3. Qubits and parallel universes. 4. The business and security race. 5. The challenge of decoherence. And finally, 6. Curing diseases and beyond.
Section 1, the evolution of computing. It's kind of crazy when you think about it, right? Our fundamental need to calculate and count has been driving human ingenuity for literally millennia. We didn't just wake up one day with supercomputers in our pockets. Stage 1 was the analog computer. Picture this. As early societies grew, people needed to track things, like how much livestock they had or how much profit they were making. So they used sticks and bones. But then, 2,000 years ago, this remarkably complex machine called the Antikythera mechanism was built specifically to map the motion of the moon, the sun, and the planets. Fast forward to the 19th century, and Charles Babbage builds the ultimate analog computer out of hundreds of gears and levers to calculate longitude and interest rates. Then, World War II hits. Babbage's mechanical gears just weren't fast enough to break German codes. So Alan Turing steps up and creates the digital standard, the Turing machine. And that sparked today's digital revolution, operating on zeros and ones at the speed of electricity through transistors. But looking ahead to the future, visionary physicist Richard Feynman asked a really profound question. How small can you actually make a transistor? The answer? An atom. Which brings us to Section 2, enter the quantum era. Let's put these two eras head to head. Digital computers, like the device you're probably using right now, are built entirely on transistors. They understand reality in a super rigid binary way. It's just zeros and ones, on or off, and it's all trapped within our single universe. But here's the thing, reality itself isn't based on zeros and ones. It's based on electrons and particles that act like waves. Quantum computers actually embrace this. They compute directly on atoms. So instead of just being on or off, they compute on literally everything in between. And as we'll see in just a second, this requires a completely new kind of math, because these machines are essentially tapping into an infinite number of parallel universes. Mind-bending, right? Section 3, Qubits and parallel universes.
Okay, get ready, because this is the real aha moment of our explainer. To wrap our heads around how a quantum computer gets its almost unbelievable power, we have to look at a famous thought experiment, Schrödinger's cat. Imagine a closed box. Inside, you place a cat. Now, is that cat dead or alive? Well, according to quantum mechanics, until you open that box and look, you actually have no idea. The cat is alive and dead at the exact same time. The universe has essentially split right down the middle. In one reality, the cat's alive. In the other, it's dead. It exists in both states, and honestly infinite other states, like maybe it's playing or sleeping, simultaneously, until you actually make a measurement.
And that brings us to a massively important concept, superposition. A quantum computer leverages this exact principle. Because electrons can be in two places at once, a quantum machine doesn't just calculate one single path at a time like your laptop does. No, it computes across an infinite number of parallel universes simultaneously. It's exploring every possible state, every single possible answer, all at once. And that right there, that is the secret to their absolutely unimaginable power.
To really put this into perspective, let's talk numbers. With digital computing, we measure power in bits, spin up or spin down, 0 or 1. Today's massive digital computers use billions of bits. But quantum computers use what we call qubits, which represent all those infinite possibilities of an object spinning between up and down. Right now, the latest generation of quantum computers can model a few thousand qubits. But the ultimate goal, the absolute holy grail of this technology, it's 1 million. When we finally hit 1 million qubits, we are going to vastly exceed the computing power of any ordinary machine on the planet. Moving into Section 4, the business and security race.
With that kind of staggering power on the horizon, Dr. Michio Kaku offers a really stark warning.
He says Silicon Valley could become the next Rust Belt. Just think about that for a second. That is an existential threat to the biggest tech players in the world right now. If they fail to join this quantum race, those massive digital empires they've built could become totally obsolete. They could literally be hollowed out, just like the heavy manufacturing industries of the past. And the main reason for all this panic is encryption. Quantum computers have the potential to crack almost any code that's currently based on digital tech. Our entire digital world relies on encryption that would take traditional computers millions of years to break. A quantum computer could potentially shatter it in moments. This is exactly why intelligence agencies, the FBI, the CIA, along with basically all national governments, are watching this like hawks and pouring vast resources into it. The first to perfect this technology doesn't just get a faster calculator, they get a tool capable of bypassing all current global digital security, completely transforming the global economy in the process.
So, Section 5, the challenge of decoherence. Now, you might be wondering, if these things are so great, why don't we have them everywhere yet? Well, creating a working quantum computer is an incredibly delicate, honestly frustrating procedure. The road to quantum supremacy is definitely not a smooth one. Step 1 requires coherence. Because we're computing on atoms, the particle waves have to vibrate in perfect, flawless unison to actually perform calculations. But then we hit Step 2, noise. The absolute slightest interference from the environment causes decoherence. The vibrations fall out of sync, everything vibrates at a different frequency, and the whole calculation instantly collapses. To fix this, scientists resort to Step 3, extreme cooling. They have to drop temperatures down to near absolute zero just to slow everything down enough so it can vibrate in perfect unison again. It is astonishingly difficult. And honestly, this brilliantly illustrates a pretty humbling truth. Mother Nature is still fundamentally way smarter than us. While we're in labs struggling with super-cooled equipment just to keep a few qubits stable, nature solves this problem every single day. The actual basis of life on Earth, photosynthesis, is a quantum mechanical process. Plants achieve quantum coherence at room temperature without any extreme cooling at all. Nature flawlessly uses quantum mechanics to sustain life, which just shows us that overcoming decoherence without absolute zero isn't impossible. We just haven't cracked nature's secret yet. Finally, Section 6, curing diseases and beyond. While those scientific hurdles are very real, they pale in comparison to the benefits that are waiting to be unleashed. Computing on a molecular level lets us directly solve our biggest molecular level problems. Take agriculture. The green revolution that feeds the world is starting to slow down, but quantum computers could unlock the exact chemical secrets of making fertilizer from nitrogen to secure our global food supply. Or energy. They could figure out how to stabilize super-hot hydrogen inside reactors to finally give us clean, limitless fusion power. And then there's medicine. Life itself is entirely based on molecules. By perfectly modeling these incredibly complex molecular interactions, we can actually start tackling the root causes of human suffering. When it comes to medicine, this changes the whole game. We are talking about turning the medical field completely upside down. Horrific conditions like Alzheimer's, Parkinson's, and cancer are largely beyond the modeling reach of traditional digital computers, simply because those machines cannot process complex molecular interactions fast enough. But that is exactly what quantum computers do best. By computing across those parallel universes, they hold the key to modeling these exact molecular breakdowns. They could give us the tools to cure the currently incurable. Which leads us to this really profound final thought. Beyond agriculture, energy, and even medicine, there is one ultimate puzzle left. Albert Einstein spent the later part of his life desperately searching for a single theory of the entire universe, a theory to explain black holes, supernovas, and galactic evolution. The equations were so impossibly complex that they eluded Einstein, and they've eluded pretty much every physicist since. But maybe the missing puzzle piece isn't just human intellect. Perhaps the ultimate theory of everything will finally be solved and discovered within the memory of a quantum computer. Thank you so much for joining me for this explainer, and keep your eyes on that quantum horizon.